Okay, so good evening, and so we'll start this problem solving session. Okay, so today's problem will be based on state space representation. So this is an alternative method to what we have learned earlier, like a frequency domain approach. So instead of transforming using the Laplace transform into the frequency domain, we just directly work with the time domain, that is the ordinary differential equations. And the advantage of doing that is that it's like unlike the frequency approach, it's not limited to only linear and time invariant system. So nonlinear system and as well as the time varying system can also be analyzed using the state space approach. And also it's useful for multi input multi output system, where the transfer function approach will be very cumbersome for that. So for each combination you have to define transfer function. And but in the frequency domain we had like more into intuition of the pictorial representation. So we have like root locus that actually viewed how the closed loop roots are poles are varied as the system parameter is varied. Also the Bode plot, the Nyquist plot that give actually insight to its response to various frequency. So it's more like an intuitive way or a pictorial representation in the frequency domain. The time domain, it will not be that intuitive, but it's has an advantage of for computational purpose. So you can use like numerical solver to solve this and analyze this. So that advantage is there. So both approach actually complement with each other. So we'll just focus now only on the state space, and we'll solve some very simple and basic type of problem. Okay. So in the first problem, so we are given state space representation. So only the state equation is given. So it's a second order system, as you can easily see it. So the poles of the systems, the location of the poles of the system. So as we know that from the relation that the transfer function. So if Ts is the transfer function between input and output. So here the output is not given, but still let some output y equal to
Sir,
yeah.
hello.
Huh?
Recording is not started, I think. The recording
Yeah, recording I have started. Yeah.
started.
Yeah.
Okay, it is not seen on the screen.
Okay, I have started.
Probably it may be on your side only.
Okay. Yeah. Yeah, I have started recording. Yeah. Yes. Okay. So then we know the transfer function to be simply as b plus d, or using this relation, that is si minus a inverse. So any matrix inverse, we know that it's just the adjoint of that, it is the si minus a by the determinant of that. So we see that we can write it like this also, si minus a b and d into this determinant of that, and the determinant of that also in the below. So this is same here. So just we can write it this way. So I'll just write it properly here. So you can see that the denominator, okay, so it's adjoint of that. So we are using this formula. So write adjoint of si minus a, so b plus d into si minus a determinant. Then we see that in the denominator we have this determinant of that term, and we know that if we equate the denominator of the transfer function to 0, then we obtain the poles of the system. And in this case it is just this si minus a, so which are also the eigenvalue of the system if we equate them. So we see that if we take this determinant equal to 0, so this gives the eigenvalue for this A matrix. So this is A matrix, and also we see that these are also same for the system poles if we transform into the transfer function representation. So that will actually give this pole. So for this case, so we can compute this. So it's like si minus a is what? So si minus a, so it's s 1 0 0 1 minus a is 0 1 minus 20 minus 9, and its is s minus 1 20 s plus 9, so equal to this s square plus 9s plus 20 equal to 0. So then the solution will be we can easily verify this is 4 and 5 will satisfy. This is the addition of that, so s plus 4 into s plus 5 will equal to 0, or poles are at minus 4 minus 5. So very simple. So these are the poles. So then we move to the next question. So again we have a system that is represented in the state space representation with the system matrix A we given as this. So this is a third order system. So we want to find the range of value x and y. For that the system will be stable. Okay, so we can use this frequency approach. So we know that if the poles are located in the left hand side, then the system will be stable. So we'll just find for what values of x and y, the range of values of x and y, the poles will be always in the left hand side. Then we are done with that, right? So again we will just use the previous result, that is the determinant of this, that is the si minus a will give the system pole. So we can just compute the system poles once the system matrix is given. So in this case we have si minus a. Okay, so I will do here. So we have si minus a is simply then this a matrix is this. So we just subtract from it s times the identity matrix. So it will be s minus x 0 0 0 s minus y 1 0 minus 1 and 2. So this is, so we want to find the determinant of that. So determinant of this matrix, so and equate it to 0. So this is equal to, then we have s minus this. You can see that this block is multiplied with this, so determinant of this multiplied with this.
That should be s plus 2 na? Last row, si minus a.
What? Sorry?
S plus 2 na? Last element 2.
Huh.
S plus 2
sorry,
na?
yeah, s plus 2. Yeah, thanks. Yeah. Sorry. S plus 2, yeah, right, yeah. So we just take the determinant of this, multiply with this, so it's then s minus y times s plus 2 plus 1. So this equal to 0. So we just simplify it. So we'll keep this x, and this will be s square. This is 2 minus y s minus 2y plus 1 equal to 0. Okay, so then the roots are will be this and this. So for this we know that one condition will be like x should be negative, then this pole will be in the left hand side, and for this we can put one condition on y to find such that this second order system will also have poles in the left hand side. So for the second order system we can either apply like Routh-Horwitz, or we can directly also compute from this coefficient. So we'll just apply this Routh-Horwitz and see for what value of y the poles will be always in the left hand side. Okay, so we can write s square s 0 1 minus 2y plus 1 2 minus y, then this element will be this. So then for same sign, because this first one is positive, then we need also this to be positive. That means y should be either less than 2, or from that we can put that minus 2y plus 1 greater than 0, or y should be less than half. So for both condition to satisfy, we need y to be less than half, right? So these two conditions are there: x is less than 0 and y, if it is less than half, then we see that both this and this.
Applying Routh criteria you are applying.
Which one? This one?
For this one, last this particular second, first is okay. S minus x should be less than x should be less than 0. That is correct.
Yeah.
Second one, for you are applying Routh criteria.
Routh-Horwitz criteria. So Then if you write, yeah, this is a second order system. So or you can also see that this coefficient should be a positive sign. That is also fine, because if you have like a square plus something a s plus b, then we know that for second order system this coefficient should be of same sign, or because it is positive, then ab should be positive also. That is also coming from the Rauthod's criteria also. That exactly same thing.
Yes.
So then you just compute for what values both
Should be greater than 0.
Yeah. So this should be greater than 0. That means y is less than 2. Second one, we have y is less than half. So for both condition to satisfy, y should be less than half.
Correct.
So this is the condition. For that we see that x should be negative and y. Yeah. So for that, yeah. So this system will be then stable. Okay. So then we move to the next question. So then we have a nonlinear system given by two ordinary.
Basically, sir, I am not getting concept of equilibrium points.
Okay.
I want to get it properly clear, because. Yes.
So okay, so equilibrium point means intuitively it means that our system, if it remains there, it should not change. Like if we don't apply any external forces, then or keep the system there, then it should remain there. So that means the change of the state of the system should be 0 there. So its derivative should be equal to 0.
Change of system should be equal to 0, derivative should be equal to 0.
Yeah. So then
x1 dot and x2 dot should be equal to 0.
So that actually gives the point that are the possible equilibrium point. So we are not saying anything about like how its neighborhood, how it will behave in the neighborhood. We are just saying that if it is there, then it should remain there only.
Okay.
So we are not saying that it will approach to there, or it will just diverge from, like if we start from a neighborhood. So it depends on how like the system is there. So it will depend on that also, like how this equilibrium point behaves in the neighborhood, how the system behave in the neighborhood of the equilibrium point. But we know that if it is in the equilibrium point, it should be at that point. So that is because we are taking the derivative to be 0. So it means that once the point is at the equilibrium point, like what this state is in the equilibrium point, then because the derivative of the system is 0, that means its state is not changing.
So what is basically significance? That derivative of that means rate of change of variable will be equal to 0. That means it will not change.
Yeah, at the time progress, its change is 0. That means it's just staying at that particular state, whatever state it is earlier there.
Sir, x1 is at stable point and x1 dot is at stable point. Both meanings are different. X1 dot means what? Rate of change of state variable number 1. x2 dot means rate of change of state variable number 2.
Yeah, we want a whole system.
Rate of change, it will be changed, but rate of change will be same. Rate of change will not change. That means suppose one is with the rate of 1 second with 1 magnitude. That it will remain change. It will not. That means variable will change, but rate of change will remain constant.
But if rate of change is 0, then it should remain only the point. If it is at 1, then if this rate of change is 0, then means it will remain only 1 only. The value will be constant, right?
Rate of change.
I mean, if some variable x is at some constant value, then its derivative is 0. We know that means if it is a time signal, then we see that its value is always remaining at the same value only. So if it is at one value, that is if the system is at like x1 bar and x2 bar, then we see that if the derivative of both are 0, then it will just remain on that point only, x1 bar and x2 for all possible time.
Yes. Okay. Yeah. That means x1, x and x variable, state variable should be at constant value.
Constant mean it is just remaining as constant mean at the time progress, it's just remaining at the same value only.
The same value.
Yeah, it's not changing with the time. So it's a constant signal with respect to the time, constant value.
Okay, sir. Okay.
Yeah, so then solving that will give the possible equilibrium points all. So
Okay.
we see that then x2 minus x2 is equal to 0 and x1 minus x1 square equal to 0, or we have x2 uh, 2 minus x2 equal to 0, or
So x2 is equal to 0 or
x1.
x2 is equal to 2.
So from first condition, yeah, so we can have x2 can be either 0 or 2,
2.
and x1 could be 0 or 1. So all this combination will be equilibrium point. That is, one combination is 0 0, x1 is 0, x2 is 0. Another combination could be 0 2, x1 is 0, x2 is 2. Another is 1 0 and 1 2. We can see that for each of this value, these two terms will be 0, because either one of these term is 0 for one value, so both will be 0 there. So these all four will be the possible equilibrium points. So then we want to find, okay, so we want to find the linearized system about these equilibrium points, and then what is the stability around that equilibrium point. So for the linearizing system, then we compute the Jacobian. So so Jacobian is defined as, so it's a two-dimensional. So if it is a n-dimensional, then we have like f1 up to fn. Then the Jacobian is defined as simply, and there are n state variables. Then we have dou f1 by dou x1. So first function, we just take derivative with all the state variables. Then the second functional, we take the variable.
Jacobian matrix.
Yeah.
So can you tell me significance of the Jacobian matrix?
Yeah. Okay. So yeah. Fn, sorry, f2 by xn del fn by x1.
Now f1, f2 over here, f1, f2. These are nothing but equations that you are putting over there, right?
Huh. So this is
Equation that you
yeah,
have
the
shown
state
over there. There are
dynamics.
two
Yeah.
equations in
So
above case.
xi dot equal to f of I. All this argument could be like all this element of x1 to xi, xn.
So I am not getting it properly because when I read it also,
Yeah.
I am not getting it clearly. Huh?
So what it actually means that, okay, so
Huh.
so basically when we okay, so we want to linearize the system. So first thing is that this is a nonlinear system. We want to find a linear approximation of the system. So so the linear approximation, so because it is nonlinear, so when we like approximate it by a linear system, it would possible that it may not match at all, like, because we just want to linearize the system. So what we want to analyze the system around this equilibrium point. So we want to linearize, for example, if this is some curve is there, nonlinear curve is there like this, and we want to find a linear approximation. So it's not possible to find a linear approximation for that, but if you just think of one neighborhood small point, and in the neighborhood, then we can find a small linear approximation here. So you see that in the neighborhood of that, it is just very closely matching with this curve. So for example, here we want to find, we can find a linear approximation of this around this neighborhood. So in that way we want to analyze, because this is a nonlinear system, we cannot say any result for this system. So we want to find some points where we want to analyze the system, and around that we want to linearize that system. So this is what this linearization means. So basically we want to analyze the system around this equilibrium point. So what we do, we linearize the system around this equilibrium point. So then we can apply linear system theory, what we have learned, but that is valid only in the small neighborhood around this equilibrium point. So to linearize the system, what we can do, so we know Taylor series. Okay, so the Taylor series is what? So any function, okay, so it can be written as an okay, so we want to write it around some point A. Then we know that the Taylor series, it gives the approximation of this function around that point with the derivative of the system, right? So that function, so derivative plus the term, like for example, okay, so we want like f of a, so we can write it like f of x plus this a minus x double dash this half a minus x whole square and so on. So this gives approximation around this point a. So x is a variable there, so we see that if you want a linear approximation, then we just stop at the first point, right? Because these are non-linear terms, square and all other. So this first term will give the linearization or the approximation of this function around a very close neighborhood of a. So this is just for one variable. So if we do this for multi-variable case, in this case we have like n variables, then we see that here this derivative was taken with respect to x variable x. So if there are n variables, then we need n derivative, that is how this function is changing. Like this is a curve, but for example surface is there like this. So we want to find, okay, there are two directions x1 and x2, then we want to find in both directions how this function is changed in the neighborhood of that. So that will be used for this Taylor series expansion for the multivariable case. So in the n dimension also, then we need n in the n direction how this function is changing. So that actually capture from this. So it gives that, okay, at the point you are at the point x, then you want to find in the neighborhood how this function is changing in the neighborhood times. So this is basically the change, or in the linear system it is just slope plus the change in the variable. So it actually gives a measure of like how this function is changing in each direction. So this Jacobian is the first element. You can see this, the change of this variable with respect to this f1 function with respect to each of this argument. So if we multiply this with this vector x1 xn, so or the difference between them, so you see that this difference is multiplied with these things. That is what is coming in the first order system. So it gives this how this the rate of change multiply this what amount of change happening in that variable, particular variable. For example, in the x1 variable, what change happen in the x1 variable multiplied with this rate of change of this function with respect to x1 variable. So it's like okay, so can you listen? Okay. Okay, so
Mathematical point of view, is it correct, or
yeah,
I am having some?
Okay, yeah, it's more like mathematical concept. So intuitively, like I want to just say what actually it means. So I think I lost somewhere between that. So I'll just again repeat. Okay, so it just basically means that, okay, so if you just write this first order approximation, okay, so just ignore this higher order term. So the first order approximation means that okay, you are at the point x, okay, so you want to go to point a. So what is then the change of this function? So this will be just this term, right? Because in the linear term we know that it's just slope times this base. If you are like at this point and you want to reach this point, so what is this change in this? So this is just this slope, okay, times this difference, right? In the linear system case, linear for a line, this is a line. So you are at this point, you want this point, so this is the change. So this is y, so y equal to mx let plus c actually starting from, if it is not from the origin, if it is origin, then this c is 0. Okay, so we see that the change in this y direction will be what? Then slope times this x value, right? This so this is, so you are changing in the dependent coordinate. This is a minus x. So what is this change? Plus the slope of this function with respect to that dependent, independent coordinate, this x. So it's like how much you want to change and what is this effect. Like this rate of change actually gives like how this function changes with respect to this x variable, right? This derivative, that is the dou f by dou x1 means what? So it's just a change of this function with respect to x1, like how it's changing. So if x1 has changed like a small amount in the neighborhood, then what will be the then effect in the original function? It will be the rate of change times this x. Is that clear or it's just confusing?
सर कंफ्यूजन हो रहा है मेरा एक्चुअली
Okay.
मैंने पढ़ा भी था थोड़ा लेकिन फिर भी कंफ्यूजन ज्यादा हो रहा है
Okay,
मुझे
so-
मतलब क्या है
Huh. So what I'm saying
वो
is,
रट्टा मार के कुछ
okay, so
हाँ.
if f is like, okay, let f is function of x1 x2 for example, then
okay देयर आर टू वेरिएबल्स
हाँ, two
x1 x2
variables.
आर स्टेट वेरिएबल्स
So then
like in our above case we are having two variables
two variables, then then this
so our matrix will be of only first two rows
first two rows.
first 2 by 2 matrix
So if
correct 2 by 2
f1 and then will be
for
another
above
f2.
example that we have taken
To this. So like I'm just saying what intuitively it means. Okay, so this is what del f by dou f by dou x is, how this f variable changing with respect to x, right? So derivative means only
X.
that thing. So
Yes.
this gives like how this, because f1 is function of both x1 and x2, so that's why we are using partial sign. So that is the partial change is happening because the total change will be by the both variables. So only by
Both variables,
yeah,
yes.
for one variable there will be some partial change in the function. So we are just denoting it by this symbol. So instead of this dou y dou x, if it is just one
Okay.
variable, so for multivariable we just use that symbol for partial, like because it is a function of many variables, so for each variable there will be some partial change. So this partial change will be given by this ratio, that is how this function is changing with respect to that particular variable. Then if that variable is changing by some amount, in this case like that, then we just multiply this rate of change with that, right? So because this is the per unit change, for example this is just the per unit change of this function. So the total change will be then what change this variable x1 is occurred, that should be multiplied to give the total change.
yes
So like
so we have to multiply because
yeah,
effect of 1 plus effect of 2 now when you are doing dou f x1 dou f1 by dou x1
huh,
what you were considering doing for the state of x2 at that time
so like this change is like per unit change, right? So like for each change in the x, what is the change in the f function? So
okay at that time x2 state we are not considering
yeah, x2 we just consider it as like a constant term, like we
Constant
keep
term,
x2
okay.
constant and then vary this x1 and see what is its effects. So it's like
yes sir, that means dou f1 by dou x1 is considered when x2 is constant then
Yeah.
we are considering dou f1 by dou x2
huh,
by considering x1 is constant
yeah,
then how you are multiplying then you have to
Okay.
add it na?
yeah, this multiplied, then you have to add this, right? Like this.
Okay.
Sorry, this
That means again you are considering over here as a system is LTS. You are considering as a LTA.
yeah,
system.
because we want linear system only, because we know linear system theory. So for this non-linear, what we can do is that we approximate that system around some neighborhood of one point, and then just approximate this by a linear system.
At that we have to go towards linearity only.
Then we can deal with whatever tool we know in the linear system, we can just directly apply and get the result. At least we can say in the neighborhood. We cannot say like
Neighborhood.
for a whole range, because this is just a non-linear function. We can say in the small
Small
neighborhood
part.
how it's gonna behave. So
Okay.
so the idea is just from this Taylor series. So from this only it's coming. So Taylor series is just an approximation. So this is the first order approximation. If we take the second order term, this is the second order approximation, and so on. So we see that for linearity we will stop at the first term because the other term are non-linear. So we stop at this point. So we see that if a is very close to x, okay, so then the difference power will be very small, right? Very small. So it's positive, like it can be positive or negative, but its magnitude is
Yes.
very small, right? It's like very small, like a small number epsilon, and very close to zero, or I can very close to 0. So I see that the higher order terms will be very close to 0. So only the first term will remain. So if a is very close to x, so we see that in the neighborhood of that point we can apply this first order approximation there. So okay, so we'll just apply that thing and see what actually this linearized model will be there. So first, stability, we just need the A matrix. So this A matrix will be then what? So we'll just use this Jacobian to compute that. So this block will be this for this case, because we have a two second order system, so it will be 2 cross 2. So and this is the okay, so this is f1 and this is f2. So we can just simply apply this partial derivative, and write this A matrix. So okay, so this is this term, this is first x1 derivative will be 0, on x2 it will be 2 minus 2x2, and for this is 1 minus 2x1, and this is 0 because the second term is not dependent on the x2 variables. Okay, and we see that this we want to analyze in the neighborhood of this point. So the equilibrium point we found 0 0 0 2 1 0 and 1 2. 0 2 1 0 and 1 2. We just substitute that value, that is x1 and x2 for A matrix, then we can find that A matrix value at that. So for 0 0 it is okay, so A will be, so I will just write 0 2 1 0, for this is 0 minus 2 2 1 0, it is 0 2 minus 1 0, and this is 0 minus 2 minus 1 0. Okay, so then to find its behavior around this neighborhood, then we just analyze these eigenvalues. So again we can compute this eigenvalue using this Si minus A determinant equal to 0. So we see that for this and this, then it will be what? S, this will be minus 1 minus 2 minus 1, and this will be S, this will be S, this will be 2 and 1. So both are same sign. So for the first and the for the first and the last,
Jacobian matrix, and this problem is very difficult to understand. I also read it, but still I am finding. अभी A matrix जो आपने निकाला है ऊपर का A matrix, matrix A in above that matrix A. Can you scroll it to A?
Okay, so which one? A matrix. Okay,
A matrix, this one, upper one, this one. How you calculated this matrix?
Okay.
2 minus.
Okay, so I'll just write.
Yeah,
I'll write in detail. So dou f1 by dou x1, dou f1 by dou x2, dou f2 by dou x1, dou f2 by dou x2.
Yes.
And f1. Okay, so f1 equal to, we have 2x2 minus the first one, x2 square.
2x2 minus x2 square.
And f1 equal to f2 equal to x1 minus x1 square. So then we take the partial derivative of that. So the first term will be, then it does not depend on the x, so it is 0. For x2 it will be 2 minus 2 x2, and this is x1, then it will be 1 minus 2 x1 and 0. So this is how we obtain that A matrix.
Yes, yes, yes. Okay.
So then we just put this eigen values, this is equilibrium point, right? So x1 x2 value are these. So
Equilibrium point that we calculated in initial stage,
yeah,
and
in the
x1.
initial stage. So we just use that value to find what is this a value there, because we know this x1 x2 value. So we just substitute that x1 and x2 in this matrix, and we obtain all these a matrices for each of these equilibrium cases. And then we can analyze the eigenvalue of each one of the matrices, like for each equilibrium point.
Yes, yes.
And then we
yes.
can comment about like how it's actually behaving in the neighborhood of that. So for example, in this case we have s square plus minus 2 equal to 0, so or s square equal to 2, so s equal to plus minus root 2. So we see that one is positive and one is negative. So it's like in one coordinate it's actually stable, like it will be reaching this equilibrium points because of the negative sign. So in the other coordinate it will be, you know, positive means it diverging. So we cannot say, or it's just unstable because both are not in the left hand side. So the around this equilibrium point the system is unstable, right, because of one positive
That
value.
means determinant of S7 you have to consider A as this individual matrix.
A is the individual matrix for each of this equilibrium point. We compute this determinant of this is. So from then first case it is just s minus 2 minus 1 s determinant. So it is s square
Yes.
minus 2 equal to 0. And
Yes.
for this case also the same thing. Just it will be s 2 1 s, right? So that will also give the same thing. The last case also. So in the middle case we have,
If ESC is plus or minus root 2, then plus means is right hand side. It will be unstable.
yeah, unstable. So unstable means it's not at that equilibrium point, because in the equilibrium point we know that it's going to remain there. So if we just perturb simply from that equilibrium point, then in that neighborhood how it's behave, like it will approach that equilibrium point or not. So in that sense it is unstable around that equilibrium point.
Yes.
So then for this second and third case we will see that it is just s square plus 2 equal to 0, or s equal to plus minus j, this imaginary roots. So for this imaginary root, then this is like it will have the oscillating nature, that is it will just if you also,
but they are non-repetitive, so it will be at the equilibrium point marginally.
yeah. So for this you can also see the lecture video. So there I think the pre-predator model was analyzed for this kind of system. So it's called center. So it's just non-linear terminology. So this equilibrium point is also called center. Then it can be stable or unstable depending on how this actually is approaching that center or not. So we'll not go there. So in the lecture video I think there is some small coverage of that. So because this is oscillating, so so in the pre-predator model, if you remember, so this is the equilibrium point. That means this will just oscillate around that, something like that. In the lecture video you will see. So this is for the imaginary root. So it will, if it is starting at the equilibrium point, it will remain in the equilibrium point. But around that, it will, because of this complex conjugate imaginary root, it will have oscillating nature. So yeah, so in the lecture video it's actually covered in detail, so you can see there. Okay, so then we can move to next question. So again we have a system, so it is just a first order system, so it's easy to comment on that. So then we find the equilibrium point, so it will be, so 1 is 0 and x could be plus minus 1.
Plus minus 1.
So for this case, because it's just a one function, so then we just compute this dou f by dou x. So in this case one variable, so we can just write also df by dx, because just a one variable, so it's equal to 1 minus 3x square. So and for 0 it is 1, for either plus or minus 1 it is minus 2. So the system will be like that. So like the approximation around this 0 point, it is it will be approximated by this. So this A matrix is 1 here, so one dimension only, and around this plus minus 1 it will be x dot equal to minus 2x. So this is just a linear approximation of this thing around this equilibrium points.
Yes, sir, yes.
And you can easily now comment on that this is stable, this is unstable because of the positive sign, this is negative sign. Also you compute the poles of the or the eigenvalue of the system. So this for this
Now, sir,
case,
hello, sir.
yeah.
You are saying that x1 dot is equal to x dot is equal to minus 2x from the equilibrium point that you are calculating from dou f by dou x. Okay. Now you are saying that system is stable. How you are saying system is stable in that case?
Okay. So for this case, so what is Si minus A?
Now s plus 2 is equal to, how you calculated this?
Oh, okay. So Si minus A. So what will be Si minus A for this case? So S is, it is one dimension only, so it is S. A matrix is minus 2. Is it clear?
Si minus a cannot write down it
Si
as
minus
Si
A.
minus
Okay,
a.
so I'll just,
Because I am finding some difficulty in this particular parameter only.
okay, so
Otherwise, I am able to understand.
Yeah, so it's just one dimension thing. So
One dimensional
so
thing.
A
Yes.
matrix will be what then? Minus 2. A equal to minus 2 only, right? So you can also write it a matrix form also like this.
Okay.
So then Si minus A will be what? S minus,
S plus it will be
yeah.
S plus 2 in that
Yeah.
case. Yes.
So and determinant is also
One
same.
dimensional matrix. One dimensional matrix. Okay.
Yeah, so this S equal to minus 2. So this easily you can see from the
This is
negative
not-
value also. For one dimension case it is easy. So this is
Yes.
also eigenvalue is also minus 2, pole is also minus 2, and so it's actually stable around that point. But for this it is positive.
But for one, it is unstable.
Yeah, it's unstable around that equilibrium point.
Totally, it is unstable. What we can say is totally it is unstable because one is
Yeah.
unstable for one.
Yeah, so it's around, it's unstable. So around this equilibrium point. So as we say that if it is in the equilibrium point, it will remain in the equilibrium point. But what happens in the neighborhood of that equilibrium point? How it's behaving? So around that it is unstable.
Yes.
Okay. So yeah. Then okay. So we have given state transition matrix. So then what will the system matrix of this? Okay. So we know the state transition matrix, okay, which is also Si minus A inverse. This is also same thing. So we have adjoint of Si minus A. So this is state transition matrix 5. This by determinant of Si minus A. Okay. So then we can easily see that from this we can take common the denominator term S plus 6 1 minus 5 S. So this is then equal to the determinant of Si minus A, and if we equate it, then we will obtain the pole of the system. So the poles are 5 and 1, S plus 5, S plus 1, 6, yeah. So minus 5 and minus 1. So these are the poles. Then okay, so one approach will be like for each of this matrix we compute this state transition and compare. So another easy approach will be, okay, so we know that the sum of the eigenvalues of a matrix, so these are poles and also eigenvalues. So eigenvalues of a matrix is equal to sum of its diagonal element, which is also called trace. Okay, so this sum of this eigenvalues, this is eigenvalues if lambda I, or this summation will be equal to the trace of this matrix. So trace means if we just add this diagonal elements, so this is actually called the trace. So it's a property of the matrix, that is this eigenvalue summation will be equal to the trace of the matrix. Okay, so then the summation of this eigenvalue is what? For these two cases it is minus 6 minus 6. Then we just see for which matrix this trace, that is the summation of this eigenvalues, is actually minus 6. Yeah, so for the D, so we see that this D is the correct answer. So you can also verify for that also and see. So it's also easy to check also, because Si minus A means Si minus A will be what? S plus sorry, s minus 1 5 s plus 6, right? By the determinant is already this one, so it is s square plus 6s plus 5. Okay, sorry, let me write properly. This is just the adjoint of that. Okay, so I will just write here. Space. Yeah, I have space here. I can write that. Okay, so for this matrix, so last matrix, so what is given? A equal to 0 1 minus 5 and 6 minus 6 minus sorry, minus 5 minus 6. So first we compute this si minus a, which is s minus 1 5 s plus 6. Then the state transition matrix is what? Just this inverse of this. So it is adjoint of si minus a by determinant of si minus a. So determinant of si minus a is this one. This term we already computed here. This term by comparing, or we can also easily check also that from this also. So this is s square plus 6s minus plus 5 equal to 0. So this is the determinant. So okay, just write clearly also. So determinant of this was si minus a determinant. So from this matrix it is easy to check. This is what? This multiply with this element minus this one, right? So s into s plus 6.
So denominator of every component is s square plus 6s plus 5 only.
So
Every are calculating over here from this si minus a determinant.
Yeah.
Same is denominator for all these components.
Yeah. So that is because in the denominator we are dividing this si minus a determinant, right? So there could be some cancellation of factor. If we don't cancel, then it will be just this. So because this inverse is adjoint of a by determinant of si minus a, so in the denominator we always will have the si minus a determinant, unless there is some cancellation for each term. Okay, so we'll see also some cancellation can occur, but if not, there is here we see that there is no cancellation is occurring. Each of the term we can take common of that first term. So then this is the adjoint of that, and this is the determinant by just comparing that. Is that clear or?
Yes sir.
Yeah. So I'm just verifying that okay, this last result is also correct. Okay, so I'm just computing the state transition matrix for the last matrix A. So for that, then we compute this si minus a inverse. So for that, adjoint of this by si minus a determinant. So adjoint of this, from this we can compute this adjoint is what? S plus 6. For 2 cross 2 matrix, computation of adjoint is simply you swap this diagonal element and take the negative sign on the off diagonal element. So this is. Then you see that dividing that it will give this result, this one.
Yes.
Yeah. So in other cases like for higher order matrix, then you have to find this minor and then find this cofactor and take that transpose of that. Okay. So for higher order matrix, so you may have known like how to compute this matrix inverse. Okay. So you just apply that. For 2 cross 2 matrix, so it's direct.
Very simple. Yes.
Yeah. So then. Okay, so we move to the next question. So we are given a state and output equation. Okay, so we want to find. Okay, we want to find like this dy by dt. Some initial condition are given at the time, initial time. What will be there? Okay, so we see that. Okay, so from this state output equation, y is what? Y is equal to x1 plus x2. If let's just multiply these two matrices, so it is x1 plus x2 y. So then we have dy by dt is what? dx1 by dt plus dx2 by dt.
Dx by dt.
Yeah.
x1 dot and x2 dot.
So from here we see that x1 dot and x2 dot is what? So x1 dot is x1
dot is x1 minus x2
and x2 dot is
x2 dot x2
plus u. we just put
Plus
this thing in
plus
this
u
equation.
hat.
So we have what? dy by dt equal to x1 dot plus x2 dot.
So I can put the values of x1 dot and x2 dot from our
x1 minus
equation.
x2 plus x2 plus u. So it's just simply x1 plus u.
Yes.
And so dy by dt at time 0, t equal to 0 will be what? Then x1 plus u. We just put t equal to 0 at that value. That is x1
Yes.
0 plus u 0. And
Yes.
this is given 1 and this is given 0. So it is just
Yes.
1 plus 0, so it is just 1. So this,
One.
yeah,
First
very,
option.
yeah. Okay. So then we move to the next question. Okay, so a system is actually given by this state equation and the output equation. Then what are the poles and zeros of the system? So what we do is just we find the transfer function. Once we find the transfer function, then we know the poles and zero. So that's all. So we'll just find the transfer function of the system. So for that we just write this A B matrices for this. So A matrix is what? So as you can see from this, minus 4
Minus
1,
4 minus 1.
this
2 minus 3.
3
X b is equal to 3 5, correct.
1
Y is equal
2.
to 1 2.
Yeah. So this is C matrix. Then we know the and D matrix is at 0. So
D is equal to 0.
the transfer
Yes.
function is, we know, C Si minus A inverse
B plus
D.
where B is equal to 0.
Yeah. So we just compute then Si minus A inverse first. So Si minus A first we will write Si minus A.
Inverse.
So it will be S plus 4 1 minus 2 S plus 3.
Yes. The determinant of this,
Yeah.
it will be
It's correct, right? Minus 1 2 so then determinant of that Si minus A will be what?
a square plus 7s plus 12
Yeah.
plus 2. So it's plus 2.
Yeah.
So it will be a square 7s plus 14.
Yeah. Then we compute the adjoint of Si minus A. So it will be S plus 3 S plus 4 minus 1 2. Okay.
Minus 1.
So then Si minus A inverse will be adjoint of Si minus
Adjoint
A,
determinant.
determinant of Si minus A. So it will be in the denominator, it will be S square plus 7S plus 14. So we'll just keep this. And the adjoint we have is S plus 3 minus 1 2 S plus 4. Then transfer function will be what? We just multiply C into this term, which you have computed this. So I'll just write C value also. So C is 1 and 2. Sorry, this is C, right? C.
1 and 2. Yes.
1 and 2.
Y is equal to 6. Yeah.
1 and 2.
And 2.
I'll just take this common as outside because this will remain there.
Plus 7s plus 14.
So S plus 3 minus
Plus
1
3
2
minus
plus
1.
4 and D matrix is 3 5.
2 by 2 matrix with 2 5. Yes.
So I'll just compute this.
Multiply first.
Minus 14 1 2. So it will be 3S plus 9.
Sir, can we multiply first two components at
Yeah,
first?
yeah, you can multiply in any order. So for matrix A, B, C, you can multiply this or you can start with also this. So it is the associative property holds for matrix multiplication. So you can multiply any order. This is fine. So it's minus 5. So 6 plus 5S.
Yes, plus 20.
So it's equal to, so we have this term 1 2, this, and this is 3s plus 4, and this is 5s
X plus 26.
26, and we have in the denominator s square plus 7s plus 14, and in the numerator it is 13s plus 56. So then this will be the 0 and this will be the pole, and you just solve this, then zeros will be at what point? So it is 56 by 13, so approximately
Yes,
minus 4.
138 plus 56.
So poles will be at minus
After multiplying 1, 2 with 3s, this one, no?
so I will just use this calculator to solve. Okay. So the poles will be then okay, 1, 7 and 14. So okay, minus 3.5 plus minus j 1.32. So the pole 0 is at and poles are at this point.
So this is 38 or 30? Yes.
Huh?
Yes, sir. I think it is yes. Yeah, I think it is, it looks like 38. That's why I was confused. Here. 38 plus 9 ऐसा लग रहा था.
Which one?
Yeah. In this transfer function calculation,
Huh.
1, 2 multiplied by these two matrices, na?
Huh.
Two matrices. It looks like 38. That's why I was confused.
Okay, which one? 38. Sorry. Oh,
It is 3s. 3s. It is 3s.
Okay. Sorry, this one. 13.
Yes.
Yeah.
Upper one, this matrix.
Yeah. Oh, this one 30. This one.
3s. 3s. This is 3s. 3s plus 9 minus 5.
Yeah.
Oh, so it is 3 plus 2. Then it will become 5s plus 26. So it will be 3s plus 10, 13s. 13s and 56. Correct. 56 plus 4. 50. Yes. 50 plus 4. Barabar. Okay.
So then from this you will get 0, and from this denominator you will get this pole.
Yes.
4.23. This one. Yeah, correct. Okay.
Yes.
So then the next question will be, okay, so again the transfer function. So again we use the same approach. So
yes, it is possible to solve.
Yeah. So just find this si minus a inverse. So first we si minus a will be s minus 1 3 s plus 6. So then determinant will be s square plus 6s plus 3, and the adjoint will be then what? So it will be s plus 6 s 1 minus 3, and this inverse will be then si minus a inverse will be just this determinant or this adjoint. So this is the term. Then we obtain this transfer function c si minus a inverse b plus d is 0. So then we just multiply this 1 by s square plus 6s plus 3. This is s plus 6 1 minus 3s, and this is 0 1. Okay, so and transfer function then will be 1 by s square plus 6s plus 3, and 1 and 0 1 means it is 1 and s. Then we have s plus 1 by s square plus 6s plus 3. This is the transfer function. Okay, simple. Okay. So then we have a transfer function, and we want to find like controllable and observable canonical form. So I'll just skip this approach because you can directly write also. So what to write this controllable form, what we will do, we'll write also like this. You can write it x1s by us, ys by some x1s. I just introduce. Then I will take this the denominator, and this is the numerator, and then you can just simplify for each of this expression. You take this denominator, that is you get this to this one, and you equate this one to the numerator. So this is actually covered in the lecture video. So then you use like x1 will come someone, so you take x2 equal to x1 derivative, x3 equal to x2 derivative, and then write the system. So you can directly also write from this. So it will be third order system. So x1, x2, x3, this one. Then A matrix will be what? So we see that x2 equal to x1 derivative. So this is x1, x2 and x3. Then it will be like this. x1 derivative will be equal to x2, and similarly x2 derivative is equal to x3. And then the last term, this term will come minus 1, minus 2, minus 3, 0, 0 and 1, because this u is multiplied there. So this 1 will come in the last term, x3 derivative, and the output equation will be then what? So this is 6, 5, 1, x1, x2, x3. So you can just verify this and compute this. So there is no it's not difficult. I think it is clear, right, how to compute this. So it's okay. So this will give this controllable canonical form. So how to compute this? So you just okay, so we have a numerator and denominator. We can always write it in like this form, just introducing some auxiliary variable x1. So this two term then will be equal to this one. We take the first term equal to this denominator, second term equal to numerator, then we just simplify that. So because of this s variable, we know in the Laplace domain the derivative term will come. If s is multiplied with the x, then it is the first derivative. S square multiplied with the x, it will be second derivative of x in the time domain, and so on. So we just simplify, you can write that and we can substitute that one. So already we have x1 variable, so x1 will take, then we will take this x2 equal to x1 derivative, x3 equal to x2 derivative, then you can just simplify and write. So that thing also from the transfer function you can directly also write this. So first form will be like this shifted identity matrix there, then the last will be in the reverse order, this element 1, 2, 3 in the negative sign will come, and this output will be also in the reverse direction 6, 5, 2, because this is multiplied with the x, this is x1 derivative, this is x2 derivative. So the first element should be multiplied with x1, second with the x1 derivative, so that is the x2, third will be x3 derivative, that is this. So you can just check this. Okay, this is not difficult, you can just check it. So for observable form, this matrix will be the transpose, B matrix will be transpose of C, and C matrix will be the transpose of B. Then we will go to the observable canonical form. Okay, so then we move to the next question. So we have a matrix and we want to find the matrix exponential. Okay, so we'll use like for method to obtain this matrix exponential. Okay, and we'll see that each of the method will give the same result. So it just depend on what method you want to find. So some method will be easier in one case and other will be, in the other cases the other method will be easier. So yeah, so am I audible?
Yes, sir. Yes,
Yeah,
sir.
okay, yeah. So I'll just pick the very simple one just to illustrate all this method. So first method 1. So in the method 1 it is easier. So we know that Si minus A inverse Laplace transform of that, Laplace inverse of this will give this matrix exponential. So we'll just compute then Si minus A. So this is S minus 1, 0, S plus 2. So determinant is S square plus, just keep it simple, you just, because we will factorize it, S into S plus 2. So this is the determinant, and adjoint is adjoint of Si minus A. So this is determinant of Si minus A. Adjoint is S plus 2, 1, 0, S. So then Si minus A inverse is adjoint of that by determinant. So it is 1 by S into S plus 2, S plus 2, 1, 0, S. So it is equal to 1 by S 1 by s into s plus 2, 0, 1 by s plus 2. So we will just factorize that. So first term is 1 by s, second term will be 1 by s minus 1 by s plus 2. So this is the 2, so half times this is 0, 1 by s plus 2. So this is the si minus a. So we just take the Laplace inverse transform of that. So then first term 1 by s, the Laplace inverse is 1. Second term 1 minus e to power minus 2t, 0, and last term is minus 2t. So this actually gives this matrix exponential term. Okay, so this is method 1. So we'll use the method 2 to compute the same exact matrix exponential. So method 2 actually deals with diagonalization of this matrix. Okay, so for if a matrix is diagonal, then we know that its matrix exponential will be what? So for example, a matrix is a1, a2, a3, all are 0. Then the matrix exponential will be what? For this, it will be a1t, a2t, a3t, but all elements are 0, like that. So this will be the eigenvalue. So that will actually come in the diagonal element. For diagonal matrix, the matrix exponential is very simple to compute. So I think you have already seen this method. So to compute that, we'll find this eigenvector that will diagonalize this matrix. That the diagonal matrix will be D. Then we know this. Then this matrix exponential will be then what? So we just e to power dt p inverse. So this is this matrix exponential for the diagonal matrix. Okay, so for this case, so what is this eigenvalue? One is 0 and one is minus 2, right? So this, okay, we just equate this determinant to 0. Then the eigenvalues are at what? 0 and minus 2. So the diagonal element will have 0 and minus 2 as the, for this 2 cross 2 matrix, the diagonal matrix will be what? 0, minus 2, 0, 0. So its matrix exponential will be what then? E to power 0, 0, 0, e to power minus 2t. So it is equal to 1, 0, 0, e to power minus 2t. So only thing is left that we have to find this P matrices. So P matrix will be what? This eigenvector will be the element of that. So how to find that eigenvector? So we know that the eigenvalues will be like this, which will satisfy this condition. Like, so eigenvalue will be what? So this will satisfy this matrix condition, or this is also same as when you write this x equal to 0, then you find that this determinant equal to 0. So this condition actually gives this result. So we will use this to compute the eigenvector. So eigenvalues are what? So one is 0 and another is minus 2. Okay. So for first case, we see that 0, 1, 0, minus 2, x is x1, x2 equal to eigenvalue we put 0, x1, x2 equal to 0, 0. So this comparing first element, it will be x2 equal to 0, minus 2, x2 equal to 0. So we see that x2 equal to 0 and x1 is free element, so we can take any value for x1. So we'll just pick 1 and this x2 value 0. So this is one eigenvector. So another eigenvector will be what? We'll again use this relation x equal to lambda x, x1, x2. Now we take the eigenvalue to be minus 2. So that implies that x1 equal to x2 equal to minus 2 x1 and minus 2 x2 equal to minus 2 x2. So the second equation is actually trivial, and from first equation we know the relation between x2 and x1. So we can arbitrarily pick x2. So we just pick x2 equal to some value, so let minus 2, then x1 equal to then 1. So this second eigenvector, so this is correspond to lambda equal to 0. So lambda equal to minus 2, the eigenvector will be 1 minus 2. So then P matrix is 1 0 1 minus 2. That is, we just write this x1 and x2, this eigenvector. x1 we have obtained this, and x2 we have obtained this, so we just write this. So this is the P matrix. So is it clear?
Yes sir, yes sir.
Yeah. So P inverse will be then what? So P inverse will be, determinant will be minus 2.
Minus 2 only.
Yeah. So and this will be 2 minus 2 1 minus 1 0. So it is equal to 1 half 0 minus half. Then e to the power at, that is the matrix exponential of the original matrix, is simply p e to the power dt p inverse 1 1 0 minus 2, and e to the power dt we have computed this one for diagonal matrix. So 1 0 0 e to the power minus 2t 1 half 0 minus half. So it will be 1 1 0 minus 2, and it will be 1 half 0 minus half e to the power minus 2t equal to 1 half 1 minus e to the power minus 2t 0 e to the power minus 2t. Okay, so this is exactly what we have obtained in the first case also, this one.
Yes.
So this is exactly equal to this one. So next we will use the third method, another method to compute this. So this actually based on the Sylvester's interpolation formula. So what it says that, okay, it is just not limited to matrix exponential, it is valid for any function. Okay, so if you are given some function form, so this function form can be of this form also. So for any function form f of at, this formula is valid. Okay, so this actually what, so first we compute the eigenvalues of the matrix. So let n for m order system or n order system, there are m eigenvalues, m order system. So then what we do, we just write this matrix first, lambda 1 lambda 1 square up to lambda 1 m minus 1, then this function f of lambda 1. So we want to find this f of a t form. Okay, then this function is given, so in this case our e to the power a t form. Okay, so we'll write this function there. Then similarly for other eigenvalue we will write lambda 2 m minus 1 f of lambda 2, and so on up to 1 in the last row we will just a. So first element is in place of I, sorry 1, it is I, then a square a to the power m minus 1, and we will put this f of a equal to 0. Then we just solve for f of a, this determinant. Okay, so for this simple case, so we want f of a t equal to, so it can be t lambda t, function of time also. So we are taking e to the power a t. Okay, and we have taken eigenvalue, we have found that eigenvalues are, one is 0, another is minus 2. So we will use this in this case. So we see that first is 1, then it is lambda 1, it is, and it is e to the power lambda 1 t, and 1 lambda 2 e to the power lambda 2 t I a e to the power a t, and this determinant should be equal to 0, and we just simplify that and we will find e to the power a t. So first, because we are given this value, we just substitute that. So first element is 1, it is 0, e to the power 0 t, so it is just 1 0 t. So this is 1. Second row, first 1, lambda 2 is minus 2, e to the power minus 2 t. Third it is I, a e to power at equal to 0. So then you just expand this determinant, so it's equal to then what? So we have here this times this, so we have 1 times this small sub block, so minus 2 e to the power at minus a e to the power minus 2t, and this 1 times this sub block, this red one times, so it's a minus plus 2i equal to 0. So this implies that e to the power at equal to half a plus 2i minus a e to the power minus 2t. So we just put half. A matrix is what? So we have 0 1 0 minus 2, 0 minus 2 plus 2i will be 2 0 0 2 minus a 0 1 0 minus 2 times e to the power minus 2t. So just simplify that, half that will be 2 1 0 0 minus 0 e to the power minus 2t 0 minus 2 e to the power minus 2t. So 1, second element will be half times 1 minus e to the power minus 2t 0, and it will be e to the power minus 2t. So again we see that the same exact things what we have already obtained, we are getting the same result. Okay, so the last method will be method 4. Okay. So method 4 will be, okay, so first one things to obtain, so we'll just already we have computed in the method 1. We see that this denominator of si minus a is in the denominator, right? This determinant of si minus a will be in the denominator because of this inverse. So once we find this eigenvalue of the poles, then we know that it will remain in the denominator term, right? Is there the determinant. So when we take this Laplace inverse transform, we know that one factor will be what? Okay, so I'll just write here. So si minus a, we obtain this s plus 2, right? So when we take this si minus a inverse, we know that adjoint of si minus a by determinant of si minus a. We see that in the denominator we have this si minus a, so it will be some form of this, right? For this case it will be s plus 2, and the above term will something that will, we can always factorize this, so it will be a matrix with some, so it will be a matrix with some term will be there. So let it be denoted by a1, some, not a1, and just denote some, it could be also s term also come there, right? So how we will denote it? Okay, some function will be there, f1 something, and okay, so f1 by s into s plus 2. For the second order, what will be this? Of this form will come 3 by s plus 2 f4 by s into s plus 2. This form will come, this inverse. So we will not exactly compute that form, but we know that in the denominator we have always this term, the determinant of si minus a. So for each term, when we take the inverse Laplace, we have to partial fraction of that term, right? So we will have some term like a by s plus b by s plus 2 for each of this element. Then we can take the inverse Laplace transform. So it will be e to power 0 t, and this will be a and b e to the power minus 2t. So we see that we will have of this form each of the element of this matrix will be of this form. Is that clear?
Yes, sir. Yes, sir.
Yeah. So, but only things that are unknown is this coefficient, right? But we know that this term will come as an eigenvalue. So the eigenvalue are 0 and -2. So this will come in the Laplace inverse transform. But only this coefficient we don't know. So what we can do is that we can assume this form to be e to the power 0t, okay, plus some k1, let k2 e to the power -2t, then k3 e to the power 0t plus k4 e to the power -2t, k5 e to the power 0t plus k6 e to the power -2t, k7 e to the power 0t plus k8 e to the power -2t. Okay, so we can assume of this form, but these are actually coming from the eigenvalues because of the Laplace transform. Each of the term in the matrix can have this form, where k1 k2 are unknown, so we have to find this k1 and k2. So for that, what we will do, we will use two property. So we will see that e to the power at, if we take the derivative of that, of this matrix, then it is exactly equal to this one. This implies that derivative of this e to the power at t equal to 0 will be a, e to the power 0 t is identity, so it's a matrix. Okay. So similarly, e to the power at t, if we just 0, then it is identity matrix. So we'll use these two property to find this all this coefficient, unknown coefficient k1 to up to k8. Okay. So first we will compute derivative of this matrix. Okay, this one. So derivative will be what? dy dt of e to the power at. So derivative means element wise derivative. Okay. So it will be minus k2 e to the power. Okay. So it will equal to derivative of each element. So first element will be what? k2 e to the power -2t. This one will be minus k4 e to the power -2t. This will be minus k6 e to the power -2t. Because this is 1, e to the power 0t is 1, so the first element derivative will be 0. Only for the second term it will contribute. So minus 2 times 2 times k8 e to the power -2t. And when we take t equal to 0, it will come minus 2 k2 minus 2 k6 minus 2 k4 minus 2 k8. Okay, and from the first property we see that this is equal to a. So the a matrix is given 0 1 0 minus 2. Okay, this one, right? And from the second property, e to the power at t equal to 0 will be what? We put t equal to 0 here, then it will be k1 plus k2, k3 plus k4, k5 plus k6. So we just put t equal to 0. So we have k7 plus k8, and this is equal to identity matrix from the second property. So equal to 1 0 1 0. So what we do is just solve these two set of equation. This equation, okay, so this equation and this equation. So from this we observe that, okay, k2 equal to 0. So I'll just write there k2 equal to 0, this one equal to this, k4 equal to minus half, k6 equal to this one 0, k8 equal to 1. And from this we just use this element and in this matrix and solve for other unknown parameters, like k1, k3, k5 and k7. So then k1 plus k2 equal to 1, but k2 equal to 0, so k1 equal to 1, k3 plus k4 equal to 0, k4 equal to minus half, then k3 should be equal to half, k5 plus k6 equal to 1, and this is 0, so we have k5 also 0, and k7 will be because this is 0, so k7, sorry, this is identity matrix, so it will be 0 1, sorry, yeah. So then K7 you can also verify it is equal to 0. So we will use this coefficient value in this assume form. So then what is this? E to power 80, K1 equal to 1, K2 equal to 0. So first term will be just 1, second term is 0, so 0 this one. K3 is half, K4 is minus half, so we have half times 1 minus e to power minus 2t. This term K5 is 0 and K6 also 0, so this is 0. K7 is 0 but K8 is equal to 1, so we have e to the power minus 2t. So you see that we also get the same result. So it's actually depend on like what approach you are using, but we will get the same result. So as I said, some approach will be like easier than the other. So you can just check like what approach is easier, then you can apply that approach to find this state transition matrix or the matrix exponential in this case. Okay, so is it clear? Or so I went first, but is it clear all this method? Or
it is clear, sir. Clear, yes, sir.
Yeah.
Yes, sir, it is clear.
Yeah, so you can use any method. So first method is simple. So you just find this Si minus A inverse and take the Laplace inverse of that. So that will give you the
Yes.
matrix exponential. The second approach is through this diagonalization approach. So you have to find this eigenvector, and then you know the diagonal form will what. So diagonal form will have all this element, diagonal element will be the eigenvalue of the matrix. So for that you just find for diagonal matrix it is easier to compute this matrix exponential. Then you take this similarity transform through this eigenvectors P inverse, then you get this matrix exponential form. The third approach is like using the Sylvester interpolation method. So that tells that this determinant will be 0 for any function. So then you just choose this function to be this exponential form. So then using that we just simplify this last element, that is the matrix exponential. So it is valid for any function of this matrix. So this function can be of any matrix function. So that you can simplify that using each of this eigenvalue. So the last approach is also similar to the first one. So instead of like using this inverse Laplace, you know that in the denominator you will have this eigenvalue or the poles of the system. So from this poles the transient response will be what, or the inverse Laplace transform will be, each of this element will contribute to the exponential form in this case, or this could be sinusoidal form also, right? So that's the Laplace inverse of that. So then you just assume some coefficient of that. So that coefficient you need to identify here.
Sir, hello, sir.
Yeah, yes.
Can I go to above equation?
Which one? Which one?
No, previous to this.
This one.
Si minus A inverse.
Si minus?
Upper one, I think.
Okay, Si minus A inverse. Okay, yeah.
Upper one.
This one.
Go above.
This
Previous one.
Which one?
Can you go before that?
Okay.
Okay, fine, madam. Sir. Actually, I understood it. No problem. You can go ahead, because already I understand what you discussed.
Okay. So.
And for state transition matrix, no issue as such.
Yeah, okay, yeah.
All four methods we can do it. Yes.
Okay. So yeah.
So can you share the recorded video link immediately on our chat box after completion?